Hello students, welcome to another session of online class. In today's class we will be discussing about different coordinate systems, which is very important as we study the electromagnetic waves. So our objective is to, as usual, revise what we have learned in the previous class. Also we will see how the Cartesian coordinate system, cylindrical coordinate system and the spherical coordinate system are different from each other. About revising what we have learnt in the previous class, we have discussed about cross significance of cross product. So this was a very important thing. Cross product for a triangle, if A, B, C are the vertices, then AB vector AB is called RAB and AC is RAC vector RAC. Then the area or the vector S is given by half into A cross RAB cross RAC. So this we have learned. This is very important, and the area vector is always perpendicular to the surface. So we have also seen about length vector will be along the line, area vector will be perpendicular. Area is also a vector which is perpendicular to the surface, represented by S, and volume is a scalar quantity. And we have seen the differential element in Cartesian coordinate system with the differential elements as dx, dy, dz, and we have seen 6 surfaces: dx, dy, az cap and dx, dy minus az cap. Similarly, dy, dz, dx cap minus dy, dz, dx cap, and the last one dx, dz, dy, ay cap and minus dx, dy, ay cap. So those are the 6 surfaces, and the volume is given by dx into dy into dz. So these are the things we can go through what we have learned in the last class. But in today's class we will be discussing about different coordinate systems. In that one, what we have already discussed, the Cartesian coordinate system. So we'll see the on simulation regarding this one. So this is a GeoGebra 3D calculator where you can simulate these things. So consider I want to plot a point 5, 3, 4, which is in 3-dimensional, represented here in A, represented as A. So this is the point which I want to represent in different coordinate systems. So to reach this point, I have different methods. The first one is the rectangular scale method. So in rectangular method or Cartesian method, what we have is the condition is x is equal to 5, which is a plane, right? So that is why this is called a rectangular coordinate system. So x is equal to 5 along x-axis at 5. If you put x is equal to 5, that will represent a plane, and y equal to 3, that is also representing another plane. So you got the intersection, but it represents a single line. If you intersect 2 planes, you get a line. Now this is the line which represents all this. Now I want the third quantity also, that is z is equal to 4. So if I put z is equal to 4, so the 3 planes intersect at A. So this is the point. So in order to reach to A, what I normally will do is I have to move along x-axis up to 5 units, as you can see here, right? Moving up to 5 units, I will reach this point. This point I will reach. Okay. Now if I move further along y axis, towards the direction of y. So I am moving along x, I am moving along y, and the third one I have to move along z axis. So this is how I reach a point, right? Along x I am moving, along y I am moving, along z I am moving. So that it requires three components. One is the x component, another one is the y component, another one is the z component. So these are the three components required to represent a point in Cartesian coordinate system: x, y, and z. So the direction is important. Along x is I am moving along the ax cap direction, along y I am moving in the ay cap direction, and along z I am moving in the az cap direction. So coming back to Cartesian coordinate system, if I see, I can write that I need three parameters: x, y, z. X requires ax cap, along y it is ay cap, and along z az cap. So this is the basic method how I can reach to a particular point: x along ax cap, y along ay cap, and z along the az cap. So these are the three parameters we will be using in Cartesian coordinate system. But as we move into the next coordinate system, so this is a rectangular coordinate system. So far we have seen. Now, is there any other method where I can reach to the point without going through this method? Is there any other method? So one of the method is I have to can I directly go to this point just below the point A? This is just below the point A. I am moving till that point. Okay, so I need to know that distance. Okay, I need to know this distance, and I have to move in a particular angle. So I need two things. One is this length, another one is this angle. So two parameters I require here. Still I reached this point, I didn't reach this point. I want to reach that point. So I want one more parameter. What is that third parameter? So if I want to move till that, I need the third parameter, that is z. I want to move along the z axis. So I required three parameters here. One is the length from the origin to the shadow of A. The second one, the angle which I have to move in along that line, and the third one is the the vertical distance from the plane to that point. So with these three parameters I am moving. So this coordinate system is called cylindrical coordinate system. Why it is called a cylindrical coordinate system, we will see. First let me erase this one. So why this is called cylindrical coordinate system? So if you see, I have moved this length. If I move this length in any direction, I will make a circle like this. If I don't know the value of angle at which I have to move, if I move only the length to get the shadow, I will end up with a cylinder, a circular path, right? See here, if I move without knowing the angle. So that is why this coordinate system is called the cylindrical coordinate system. So in this one I need three parameters. What are they? The first one is the length which I have to travel, the second one the angle which I have to move, and the third one the height which I have to move up. So these three parameters are called, what they are called, the first one the length which I want to travel is called rho, represented as rho, and the angle which I have to move is called phi. Okay, the angle which I have to move is called phi, and the third one, the height which I have to climb up is called z. So this height which I have to climb up is called z. So again we require three parameters. What are they? Rho, phi and z. So if I go to the next one, the cylindrical coordinate system, here I require three parameters: rho, phi and z. So what will be the unit vectors? Unit vectors will be a rho cap, a phi cap and a z cap. Now we have to derive a relationship between rho, phi and z with respect to x, y, z, which is the Cartesian coordinate system. So I am going back to the same here. Now in this one I am just disabling the z part, because z part is same in the previous one and in this case also the z part is same. But if I disable all other things other than the if I disable the z part also, what I have is this is the length rho, right? This is the angle phi, and I had in the previous one these two, u and v. So I will rotate this one such that I can see this properly. I will erase this one. I will rotate till I am getting a right angle triangle. So what are these three things? This is rho, this is phi, this is x axis, this is the y axis. So according to Pythagoras theorem, what is rho? Rho is equal to x square root of x square plus y square. What is phi? So phi, so you know tan phi. What is tan phi? Opposite by h sin y by x. So what is phi? Phi is equal to tan inverse y by x. So you got the relation, simple as it is. Rho is equal to x square root of x square plus y square, and phi is equal to tan inverse y by x. And what about z? Z remains the same. So I can move back to this one. So I can write rho is equal to square root of x square plus y square plus z square. And what is phi? Phi is equal to tan inverse y by x. And what is z? Z is equal to z itself. Correct? So this is how I reach to that point. Okay. So this is about cylindrical coordinate system. So what is the last coordinate system? That is nothing but the spherical coordinate system. If I go back to the simulation, if I erase all these things, so I want to know the cylindrical coordinate system. So let me reach the point A. So this is the circular, this one I have used. So we used two techniques to reach the point. The first one is moving like this, this and this, that is Cartesian coordinate system. The second one, start, rotate with an angle, move in this angle's direction and move up. That is the second method. So what is the third method? Instead of moving all this way Do we have any other methods where we can directly reach to that point? Okay, so if I have to directly move to that point, to the point A, what is the method I have to approach? I have to directly move, so I need to know one thing. What is that one thing? I need to know I have to reach here, so I need to know at which angle I have to, what is the length of this one, the first one. The another thing is at which angle I have to move. The third thing is at which angle I have to move with respect to z-axis, because I am not only moving in this direction. This is not the way I am doing. Instead I am moving like this. So I need two types of angles and one length. So I can depict in this one. So I need to move to the point, this one. So this is the direct movement I have to do from origin to A, but I know, if I know the length, and if I move in any direction, I will create something called a sphere. If I move from origin, I know the length. I can move in any direction, right? Not only to A, I can move with that length through another direction. So I create a sphere. That is why this coordinate system is called a spherical coordinate system. Okay. Without knowing the value of angles, if I move, I will reach out to this point. Okay. So now what are the parameters I am considering here? So I think you are clear with why it is called a spherical coordinate system. So if I consider so this is how I reach earlier, then angle phi, and I am moving. So now I need three parameters, so I can represent like this. So the first parameter is nothing but the length r. This length is called r, radius of the sphere. Now I have to set this in a particular angle. You know this angle, right? So the same angle I have to use here. So that angle is called phi. So phi is the angle between x-axis and rho. So rho is the line which we used in this system, cylindrical coordinate system. So rho, r, phi. So phi and r are there. And the third one is nothing but the angle between z-axis and the line. So the angle between the z-axis and line is called theta. Okay. So we require three parameters. What are they? The first one is r, the second one is phi, and the third one is the angle theta. So what are they? The first one, r, is the distance between the point and the origin, that is r. And the second one is the angle between x-axis and the shadow of the point. So these two lines, rho and x. And the third one is the angle between the z-axis and the r, vector r. So these are the three parameters. So coming back to the spherical coordinate system, so we have r, phi, theta. So what are the unit vectors? ar cap, a phi cap, and a theta cap. Okay. Now we want to find the relation between r and, so here itself we can see a right angular triangle. R, this is rho, this is z. So rho square plus z square is equal to r square. So I can write r is equal to square root of rho square plus z square. No, rho square we know it is x square plus y square. So remaining is z square. So r is equal to root of x square plus y square plus z square. Now what is phi? phi is tan inverse y by x. So this we have seen earlier in the previous case. And what is theta? So if I consider this right angle triangle, so this length is rho, this length is z. So from this one, theta is equal to tan inverse opposite, that is rho, which is nothing but root of x square plus y square divided by z. So we got all the three relationship. So relationship is r is equal to rho square plus z square, which is nothing but x square plus root of x square plus y square plus z square, and phi is equal to phi in cylindrical or tan inverse y by x in Cartesian, and z is equal to, theta is equal to tan inverse rho by z in cylindrical and tan inverse square root of x square plus y square divided by z. So these are the three relationships we have between the cylindrical, spherical and Cartesian coordinate system. Before finishing up, I would like to mention the direction of unit vectors of each coordinate system. So let me erase these all things. So if we see here in the Cartesian coordinate system, all the three parameters which we are using are along x-axis. The first one is along the x-axis, the red one, so that represents x-axis. So that is ax cap. So ax cap is in this direction. Along y-axis, so in this direction we have ay cap, and the third direction is nothing but the z direction. In this direction we have az cap. So this is clear, yes, for you. So along x ax cap, along y ay cap, and along z az cap. Now what is in the case of the other coordinate system, that is rho phi z. So I have vector this one, so this is not required. Okay, so here the directions are, so arrow is the direction of rho is moving here, so this will be the direction of arrow. So when rho is in this line, so this will be the direction of arrow. So arrow is radially outward. Okay, now what is the direction of phi? Phi is an angle, right? So how to get the direction of phi? So the phi is an angle, so the direction of phi will be always a tangent to rho, always anti-clockwise. Okay, so this is the direction of a phi. Now a rho and a phi are perpendicular, that is what required for us also. Now az, as usual, this is the z direction, so it is on. So three directions once again. Arrow is along the rho axis, along the rho line, or radially outward. Phi tangential to rho to the point, and z is perpendicular always along the z axis. So az is along the z axis. Now the third and the last one, So the last one we have the spherical coordinate system. So where we have directly z. So this is the direction of r. So r is moving outward. So this is AR cap. Direction of AR cap is radially outward in all direction. In the case of arrow, it was only in the plane. Here it is in all direction, three-dimensionally. And where is the direction of phi? Phi is tangential. So this is the direction of phi. So they are perpendicular to each other. And this is the direction of theta. So this will be the direction of theta, a theta cap. So these three, AR cap, a phi cap, and a theta cap. So if r is like this, AR cap is downwards, a theta cap is in this direction, a phi cap is tangential to the circle. Okay. So these three are the directions of arrow, AR, a phi, and a theta. So this is the basic thing we have seen here. So how to do this simulation. Now moving back, so we have this relation. Now can we convert a simple given point, for example 2, 3, 4 in Cartesian? I'll take a new. So if 2, 3, 4 are the Cartesian coordinate system points, so respectively x, y, z. So x is equal to 2, y is equal to 3, and z is equal to 4. So this is in Cartesian. Now if I want in cylindrical, I have rho, phi, and z. So what is rho? Rho is equal to x square plus y square, square root of, that will be root of 4 plus 9, root 13. And what about phi? Phi is equal to tan inverse y by x. So tan inverse y is 3 by 2. So tan inverse of 1.5. And z is equal to, z is nothing but 4. So this is how we convert the value from a Cartesian to cylindrical. Now for spherical, r is equal to square root of x square plus y square plus z square, so which will be square root of 4 plus 9 plus 16, so root 29. And phi remains same, tan inverse 1.5, and z theta is equal to tan inverse rho is root 13 by z is 4. This is the value. So this is how we convert one coordinate system to other. But so far we have seen how to convert from Cartesian to cylindrical and spherical. So in the next class we will see how to convert back and how to find the components in each coordinate systems. So that's all. Thank you.